Good morning, everybody. Sorry that was the last day. So our first speaker is Andrey Smirnov. He will tell us what we mean on the stable angle.
Great. Let's start. Thank you for the invitation, for the opportunity to be here, and special thanks to people who managed to come for morning session after our reception yesterday. I'm going to talk about K-theoretic limits of elliptic stable envelopes and how they can be used to construct quantum difference equations for Nakajima varieties. So I would like to start with the following motivation, is the following question. So the question is, say we know a monodromy of certain difference equation, can we reconstruct the difference equation itself? The answer is yes, in most cases. And so let's see how it goes. So let's say, as an example, I have this difference equation, very simple. Then, what is the monodromy of this difference equation? Well, I can construct two types of solutions. One solution which will be analytic in the neighborhood of 0. So it's this one. You can represent it as an infinite product but by using Q binomial theorem, you can just expand it in power series in Z. That's going to converge in the neighborhood of 0. So it's some kind of elementary hypergeometric function here. And it's a power series in Z. Alright? But there is other type of solution, so you can try to solve the same equation in the neighborhood of Z is equal to infinity. And again, you'll see almost the same infinite product, well, with some prefactor here, some kind of exponential prefactor correction, which I ignore. Essentially, it's the same, and you can use a binomial theorem again to expand it in a power series in inverse powers of Z. So it's an analytic function in the neighborhood of infinity. So it's sort of you can see these both products as the following picture. So you can sort of have a line, and each factor in infinite product corresponds to an integer point on that line. So the first product is somehow goes over the positive integers, and this one is the product over the negative integers. All right, but the factors are essentially the same. So what is the monodromy of K-difference equation? Well, the monodromy by definition is a transition matrix, which is in this case is just one-dimensional, which says how to go from one solution to another solution. Well, in this case, this is just the ratio of these two solutions, and so you can observe that the ratio of these two solutions is something. I mean, it's not a constant. It's something elliptic. That's an elliptic function. Well, theta denotes the classical Jacobi theta function here. All right. In this case, that's the monodromy. Well, let's suppose I want to solve my question the following way. Suppose for some reason, maybe from somewhere, I know the answer for monodromy. So in this case, I know this ratio of the function. Can I get back and reconstruct my difference equation? Well, the answer is yes, and there is an interesting limit. So it's a simple computation which you can do is the following. So let's pick some rational, like even real number, s, let's consider this function, this ratio of theta function, and we can consider the following limit. So we can shift the parameter z by some power of q, and then send q to 0. So I'm interested in this type of limit. So I'm not doing anything with parameter z here, so I'm just sending q to 0, so this step of my difference equation. And then the limit is kind of remarkable. It turns out that the limit is a piecewise constant function. So, so if s is not integral, you actually get some power of h bar. So here this thing denotes the floor.
Why?
Right?
Switch.
It's already turned on. Okay, so all right. Yeah. So this limit, in this limit, you kind of see some kind of wall structure. So is that it? Okay. All right. Okay, I hope that's better. Yeah. All right, perfect. So yeah, so in this limit you see some kind of wall structure, and so the limit of this ratio of theta functions is a locally constant function, which and this limit is only changing, it jumps over some walls, and in this case the walls correspond to integral points. And so if you consider the limit in between walls, so the s is not integral, then it's interesting that the answer does not really depend on this parameter z, right, at all. So you just get some power of h bar here, but once you get to the wall, you actually see some power of h bar, but you also get some function which depends on this parameter z. And well, and this function which depends on z is nothing but this function which defines the Q difference equation. So in principle, that says that considering that kind of limits, you can reconstruct your Q difference equation. And this is what I want to do, but I want to do it for difference equations arising in from Nakajima varieties, which describe the quantum K-theory of these things. And more or less, this is an example. So this example is actually a special case of that. So secretly, so this difference equation which I have here, so this is actually a difference equation for a Quiller variety which looks like this. So it's 1, 1. So geometrically, this is just a point. So geometrically, this is T star E0. So it's a point, but the curve count in this Nakajima variety, in a sense, is not real, and it gives you this function. All right. And the mirror, so this Quiller variety has a mirror. So it's a two-dimensional variety with one fixed point. And this parameter z, which was counting parameter in my example, becomes equivariant parameter of some torus, which acts on the dual side of the mirror side. And so the character of a tangent space at these unique fixed points are exactly z and zh bar. So what you see here, so this thing, this ratio, is exactly the theta function of a characters which arise on the dual side. And so geometrically, this is just the ratio of two elliptic stable envelopes in this very simple case. So this is the elliptic stable envelope corresponding to one choice of a chamber, and the numerator is the elliptic stable envelope corresponding to the other choice of a chamber. And so this is what happens in geometry. So I can use 3D mirror symmetry to write some explicit formulas for the monodromy of these equations, and then by studying this kind of limits, I can go back and reconstruct the quantum difference equations, which sometimes may be complicated. All right, so let me switch to the general situation. So the general situation is the following. So let's say I have some Nakajima variety. So by definition, this is a JT quotient of a vector space. This vector space is a representation of some quiver. So you take a quiver, you representation, the JT quotient. JT quotient depends on a choice of character, which is called stability parameter. So this is parameter theta, and your variety depends again on the choice of the stability parameter in a locally constant way. So you have some chambers, so you have a space of the stability parameters, and this space is kind of split into chambers by some hyperplanes. And your variety remains the same if you're in the same chamber, and if you go across the wall in that space, well, there is some kind of birational transformation which corresponds to the flow of an integral variety. Alright, so we have these objects, and another thing that I'm going to do my thing equivariantly, so the Nakajima varieties are always equipped with some big torus action, so I always assume that there is a action of torus A on this variety, and I will denote by letters A the corresponding equivalent parameters. Okay, so that's my notations. Alright, so how the difference equations appear in this context? So we do enumerative geometry of these varieties, namely we're going to do equivariant curve count. So for like, I need the following thing for this talk. So let's say approximately it looks as follows. So let's say I have a fixed point on the Q variety, and let's say for simplicity that the number of fixed points, the set of fixed points is just a line itself. Then I can consider the moduli space, which is the moduli space of quasi-maps from a curve P1 into the Q variety with some extra conditions. So I want the point at infinity of my curve go to this specially chosen fixed point. All right, and let's say d denotes the degree of this map, and the degree is element in a second etymology of a Q variety, which is a lattice, and then here denotes the number of vertices in a Q variety. So it's always lattice like that. Okay, so I have this moduli space, and this is it's known that it's nice moduli space. You can do enumerative geometry of that. What I mean by that is the following: we can consider Euler characteristic of this moduli space, but it's only defined equivariantly, right? So as I said, I have a action of torus A on the Nakajima variety. Well, it induces an action on the moduli space. In addition, I have a action of extra torus, which I call CQ here, and it acts on the source of quasi-map on this P1. It rotates P1, but fixes 2 points, 0 and infinity. Well, this whole torus acts on a moduli space of quasi-maps, and we can consider this type of integral. So this integral, roughly speaking, computes the equivariant number of curves in the Nakajima variety with special conditions that passes through these fixed points. So by the integral I mean equivariant Euler characteristics, and it's defined only after localization. So the result lives in localized K-theory of a point. So basically it's a rational function in all parameters you have. So it's in equivariant parameters and this extra parameter Q, which rotates the curve. So the vertex function, it's a kind of hypergeometric functions which are basically defined as a generating series for these numbers, right? So this is here a new parameter appear, z. In this context, it's just a counting parameter, right? So it counts degree. Well, I use this notation because d is usually a vector. And the important thing here is that, well, the summation goes over the effective curves, and this is the part of the construction which depends on the choice of stability condition, right? So for one choice of stability condition, you may go over some cone, say of positive degrees. For the opposite choice of stability condition, you will get some cone, you'll get some power series, say in negative power series, right? So what do we know about these generating functions, which are called vertex functions? Well, in many cases, especially for type A or affine type A Nakajima varieties, these coefficients are computable. So you can use equivalent localization to just write the formulas for them. And they're very deep in the sense that you can write many different types of localization formulas. And one of those formulas will be, just accounting over the fixed points. Another type of formulas will be some kind of integrals. And in this case, like for type A Cuvier varieties, they're going to be like Selbach integrals of type A. So I'm saying that there is a deep combinatorics in these coefficients, and there are many ways to represent them. And the Selbach integrals also appear here as the way to compute it. Another thing which is more important is that, well, this power series, they actually form a basis of solutions of some quantum difference equations, or like Q-difference equations. And moreover, it's difference equations in both equivalent parameters A and Keller parameters Z, right? So those parameters kind of enter different. So we have a power series in Z with some coefficients in equivalent parameters, which are rational numbers. But secretly, there are some interesting difference equations which this function satisfy in both parameters. And even more interesting thing is that this difference equation is actually independent on the choice of stability condition. So how can you view it? So as I said, that we have a bunch of chambers with different stability conditions, and for each chamber I have a Nakajima variety corresponding to that chamber. So we can think about it in the following way. So our Keller parameters, so these are the parameters in which my vertex functions are power series, the counting parameters. I can view them as coordinates on some torus, on the Keller torus. And this torus has a toric compactification. So the different infinities in this toric compactification corresponds to different chambers in my in this picture. And on this global thing, there is a Q-difference equation, so it's defined globally, and it's invariant with respect to toric changes, toric change of coordinates from, so say, from one point to another. So basically, it says that vertex functions form local solutions of Q-difference equations in the different infinities at that torus. So if you choose some stability parameter theta, you can construct a Nakajima variety for that choice of stability condition. Well, and the set of vertex functions will be a power series which are holomorphic, so it's an analytic function in some neighborhood on this torus. Right? So for the other choice of stability condition, you may get maybe a power series in inverse powers of that. And, but the Q-difference equation is something defined globally here and invariant with respect to change of variables from, say, Z to Z inverse. Right? This is kind of a story. And again, the monodromy of a Q-difference equation is the following question. The question is, like, you have a basis of solutions of Q-difference equations in here at one infinity, and then you have a basis at some other infinity, and the question is, what is the transition matrix from one infinity to another? Okay, so just to put it in the context of this maybe conference, let me say like one example. Say what kind of function you get if you consider the Nakajima variety given by cotangent bundle of full flag variety. The answer is that, well, you get some generating functions of quasi-maps, and this is functions that many of you saw. So secretly, this function satisfies some Q-difference equations which can be written in the form, in the following form. So this function is eigenvalue of McDonald Q-difference operators in both equivalent and Keller parameters. So it says that if you act with by McDonald Q-difference operator on the Keller parameters, you get the same function with some eigenvalue given by elementary symmetric function and accurate parameters. This function appeared many times during this conference, so this is how you get integrable systems, for example, from this type of considerations. And again, so this is kind of McDonald theory, and the McDonald theory arises when you consider flat varieties. But in general, the theory is much richer, and there are much more interesting examples showing out.
Just one question. So, is this for type A or in general?
The difference equations? Yeah, in general. Okay, so already in this example, you kind of see some symmetry between the Keller parameters and equivalent parameters. So these vertex functions satisfy the same key difference equations in both variables. But in general, it's not the case. So in general, even the number of Keller parameters is not equal to the number of equivalent parameters, and so there is no chance that the difference equations in different parameters are the same. But the symmetry, some sort of symmetry between two sets of parameters is still preserved, and it's called three-dimensional mirror symmetry. So what this three-dimensional mirror symmetry says, like in simple words, it says that have a clear variety X. Well, it's not necessarily a clear variety, so the mirror symmetry is a more general context, but anyway. So nice situation, in some nice situations you always have a other variety, which have very different geometry, and it's called mirror of X, so I call it the X trig. But, so let's say we are in a nice situation when X trig is also an intergenal variety. So I can do all the same things, so I have also some modular space of Keller parameters for X trig. And the idea is that the equivalent and Keller parameters are switched on both sides. So the equivalent parameters of this torus, of this variety, right? So those are the parameters which enter as coefficients of my vertex function, are secretly counting parameters here, right? So Z's will be the equivalent parameters on that side. Okay, and well, the geometry of this thing is very different, but the idea is that this variety has its own vertex functions, and it's form again a basis of solutions of the same key difference equations. But now the difference is that these solutions, which appear in here, was power series in Keller parameters with rational coefficients and equivalent parameters. On the other side, you get a new type of solutions, which are power series in equivalent parameters and with rational coefficients and Keller parameters. So that is the phenomenon which is called 3D mirror symmetry. And the natural question to ask, well, okay, I have some basis of solutions here, right? I have some, say, basis of solutions here, in some corner of the modular space on the dual side. There should be a transition matrix which says how to recalculate one basis of solutions to another basis of solutions. What this basis is, it has a geometric meaning. So, yeah, again, it's going to be some kind of, I mean, if you choose a set of your vertex functions, it's going to be explicitly given by some matrix. And this matrix is it's a tricky thing, right? So on that side, we have something which have a lot of poles in equivalent parameters, but is analytic in Keller parameters, right? So it's a power series in that. On the other side, the situation is switched. And so this matrix, it must have like an infinite zeros and infinite poles, so it kind of cancels the poles in equivalent parameters and make a function holomorphic in equivalent parameters. But it also adds a lot of poles in Keller parameters. Well, in general, this matrix is an elliptic thing, so the matrix coefficients of those matrices looks like a combinations, like a sum of the ratios of theta functions, which depends on all parameters you have in the game, like Keller parameters, equivalent parameters, and so on. Well, and the interesting thing is that this transition matrix is something which has a meaning in geometry. So this is what is called elliptic stable envelope. So, so this is a theorem. Well, I wrote it as a claim because some part of it, so it's like a philosophy, but I'm not sure like all the details here are proved or not. But the point is that this transition matrix, so which I call, so say if I go from this corner corresponding to x theta to some other corner on the dual side which corresponds to x shrik theta shrik, so I will denote this transition matrix by S.
For a while we didn't see what we did, but now we do.
Ah, okay. So, sorry. This is my notation if I go from this corner to that corner. All right. So, so the answer is that this matrix is the elliptic stable envelope of a variety x with the choice of a chamber. So the construction of elliptic stable envelope depends on some extra choices, and the chamber corresponds to a choice of a stability condition on the dual side. So the chamber, again, the chamber of a stable envelope is something which is, it's a choice of a corner on the modulus place on the other side. Okay. Well, elliptic stable envelopes, well, you may think about them as some kind of version of elliptic Schubert classes, right? So it's like elliptic generalization of that. And if you take a Schubert class corresponding to some fixed point, and then it's an elliptic class, an elliptic cohomology, you can restrict it at some other point, and you get a matrix. And the matrix of transition between one solution and the other solutions is exactly this stable envelopes. So what is proven in Arkham-Koff and Aganajek is that this matrix given by elliptic stable envelope has expected pole cancellation properties, right? So as I said, this matrix should cancel a lot of poles and create a lot of new poles. This matrix has it, but what is not proven is that this matrix exactly maps vertex function on one side to exactly vertex function on the other side. That is some extra work and it is true, like at least experimentally, if you put it on a computer, try to compute it in examples, that's always true, but I don't know how to prove it. All right? And there is a lot of implications. So in the paper of Aganajek and Arkham-Koff, the elliptic stable envelope is defined axiomatically, right? So given a variety, you can see the elliptic cohomology of that variety. There is a very special classes in elliptic cohomology which satisfy a bunch of conditions, which fix these classes you need. And if you kind of view it from this point of view, it's absolutely unclear that the stable envelopes on one side and on the other side are related. But from this picture, let's say I have a map which goes from the vertex functions on x to the vertex function on x shrik. And it's a stable envelope of x. But the inverse of that map, well, it's a stable envelope on a dual variety with the corresponding choice of stability condition in chamber. So this is the inverse of that. So if you believe in that philosophy, then you know that the elliptic stable envelope classes, the matrix of restrictions to fixed points on x, is equal to the matrix of restrictions inverse of that, of the elliptic stable envelope on a dual variety. And again, from this philosophy, it's kind of clear, but if you look at examples when the elliptic stable envelopes are computed, it's a very complicated identity to see from the definitions of elliptic stable envelopes, or from this axiomatic that it holds. In many cases, we know how to prove it, so probably Richard will tell us about it today, how to prove it for all varieties. But still, that is some quite complicated in general. All right. So what about monodromy? So as I said, I was interested in the monodromy of my difference equation. So I have a solution which is holomorphic in Z in some infinity, and I have a solution which is holomorphic in inverse power set Z at some other infinity. And I want to compute a matrix of transition from here to here. Well, but if I know the elliptic stable envelope, and if I know that it maps functions to vertex functions on X to vertex function on the dual side, I can compute it as follows. So I can choose some corner on the dual moduli space. I can map my vertex functions from here to vertex functions from here, and the same way for the other corner. And then the ratio of these two things is exactly the monodromy which I want to compute. So the monodromy, well, roughly speaking, looks as follows. So the monodromy of a quantum difference equation for vertex functions, I mean, is described by the ratio of two stable envelopes. So this is close to an object which we call elliptic R matrix. It's going to be elliptic R matrix of X, or via that relation which relates stable envelopes on both sides. It's elliptic R matrix of a dual thing. But anyway, so this is my monodromy. And again, so I get back to my original question. I want to construct quantum difference equations for pure varieties, but geometrically I know the monodromy of this difference equation. So I need to do the same trick from which I started. Okay, so this is my second point. Yeah, the summary of this discussion is again that quantum geometry of pure varieties, the enumerative geometry of pure varieties, these difference equations, is in a sense controlled by the algebraic topology of X and X dual, namely by elliptic homology. Well, okay, so let's go back to the question of construction of the quantum difference equation from the monodromy. So here in this slide I need to explain some known things about the corresponding difference equation. This is from my paper with Zakhankov. So I'll try to explain this paper, which is like 100 pages, in one slide. So what is the kind of upshot? So if you have an Nakajima variety X, you can construct, there exists some natural quantum affine group which acts in K-theory of these varieties. And we heard many talks, like Andrey Smirnov was talking about these constructions in general. And with this quantum group you can associate something called a quantum dynamical while group. The quantum difference equation for the pure variety can be constructed from this quantum dynamical while group. So, like in short, what you see, like the cartan of this quantum algebra is equipped with some kind of hyperplane arrangement. And this hyperplane arrangement is Picard periodic. So Picard of your variety is a lattice. So again, Picard of an Nakajima variety is always a lattice. And this lattice is kind of a lattice part of the corresponding affine while group. So it acts here by shifting alcoves. Alright, so then the construction of quantum dynamical while group, and this construction was inspired by the work of Ettinghoff and Warchenko, who first constructed the quantum dynamical while group. So it assigns a special element to each wall in this picture, so the wall separating, say, two chambers. There is a special element which we call, I guess I didn't denote it here, so let me write it. So for each wall I have a special element, I'm going to denote it BWZ. And this Z is called dynamical parameter. So in our story it's a curve counting parameter. And for each wall you have an element, kind of dynamical version of a simple reflection corresponding to that root. And in a sense, this element corresponds to a reflection across this hyperplane. All right. And so the work of Ettinghoff and Warchenko, they constructed for simple algebras, and what we did with Zakhankov is kind of try to use the same idea and to generalize it into a general context of quantum Nakajima Okay, but okay. So the long story short is that if you want to describe quantum difference equation for pure varieties, this equation has the following form. It's a matrix form, right? So it's an order 1 K-difference equation, and those things are, so this thing is a matrix. This is a matrix of dimension given by dimension of a K-theory, or like the number of fixed points in your story. And the idea is the following. So if you take your Keller parameter Z, you shift it by some character sigma. That's an element of, in this context, that's an element of a Picard group. This corresponds to a shift of alcoves. And so as I said, sigma acts by shifting alcoves in this picture. And among the chambers, there is one canonical chamber called anti-canonical chamber. So it's a chamber which has 0 as one of its corners, and it contains like anti-ample elements. So this picture is this chamber. So what you need to do, you take this chamber, you shift it by sigma, and then you choose a path which connects original chamber to the shifted chamber. And then this matrix M, which enters the quantum difference equation, is just a product over all walls which you can encounter when you travel from the original chamber to the shifted chamber. So this way you get the shift. This way you show. So this construction describes how the fundamental solution of quantum difference equation changes once you shift Keller parameters by an element of the Picard. And of course you can choose, like, you can shift it by different directions in this picture, so it's a multi-dimensional thing. And all these shifts will be compatible. So the corresponding shifts will commute, so it's a compatible system of K-difference equation. Again, and our main result in this paper with Akonkov was some explicit construction of these wall crossing operators. So basically, we gave some formula in terms of generators and relations of this algebra. So if you saw a formula, if you've seen a formula for the reflection elements in say the algebraic case, that is some kind of exponent of root elements. And yeah, so we basically wrote a formula for that in this case. Okay, so I have this picture. Then, again, if you have Q-difference equations, in a sense, they're much simpler than differential equations, because you can write a formula, you can write infinite product formula for formal solutions. So if you know this story, and if you know this difference equation, you can write the formulas for formal solutions. And here I repeat the story from which I started, but now it's multi-dimensional. So you can form some kind of solution, infinite product solution, formal solutions of Q-difference equations, which is holomorphic in the neighborhood of 0, determined by, say, positive stability condition. So what you need to do, you need to take your origin, so your fundamental alcove, and you choose a path to infinity. And by path to infinity, I mean the one which is dictated by stability condition. So the stability condition gives you kind of a direction in which you should go. And then you look at this product of all wall crossing operators. So again, from the definition, from this formula for the Q-difference equation, if you play a little bit with that, it's kind of obvious that this thing is a formal solution. It's not obvious why this infinite product converges, but if you do it in the direction of stability condition, then it converges. And there is another solution, which is kind of opposite of that. So it's a power series in the inverse powers of Z, in a sense. And it's going to be given by, again, the same kind of infinite product, but now you go from the fundamental alcove to minus infinity, again in the direction given by minus stability condition. So again, we have these two formal solutions. They are well defined, so we can compute the monodromy in this language. And again, the monodromy is the ratio of these two things. And now it's an infinite product of all wall crossing operators. So the monodromy of this equation is kind of, so this is the, I would say, matrix generalization of an infinite product formula for theta functions from which I started. And so you start from like minus infinity in this picture, you go to plus infinity in this picture, you take a product of four crossing operators. This is defined thing, and this is kind of infinite product formula for elliptic theta function. So the matrix elements again of this infinite product of matrices are elliptic functions. Again, and the question is, how would I reconstruct my K-difference equation if I know it's monodromy, right? From this infinite product representation, what you can infer is the following. Again, you can invent, you can hook up some special limit so that in this limit, only one factors of this infinitely many factors would survive. Right? So you can invent some special limit. So you take your Keller parameter, you shift it by some power of Q. And if you choose the parameter S in this shift in here to be somewhere in the wall, you can prove that all the factors in this infinite product except single one corresponding to exactly that wall would survive. Right? So so from this formal expression you can prove something like this. That the limit of this monodromy gives you a wall crossing operator. And again, this wall crossing operators is exactly what we were trying to construct in the paper with Akunkov. So we were chasing these operators. But now I can get them in a very different way without any reference to quantum group, which actually is. Yeah.
So in the univariate case, you only got the difference equation up to a scalar. That depended on sort of which wall. I mean, you're getting the original difference equation times some power of h bar. Because some of the terms in your product were not converging to one; they were converging to constants. So why do you only get like correction factors on one side here? Because you're sort of looking at one term in the middle, and everything's converging to a constant.
Well, yeah. So I left some factors here without explanation who they are.
Yeah.
But secretly, they are the products of these wall crossing operators for infinite sets. I mean, they're non-trivial, but in that story, it's kind of, you can handle that and still extract this one single.
I see. So you basically know what you have factors on the side.
Yeah.
What they are.
There are some factors here which I skipped, and so they correspond to some limits of this wall crossing operators at infinity. They are non-trivial, but again, you can handle them.
Okay, but the wall crossing at 0 is 1.
Wall crossing at 0 was 1, at infinity it's not.
That's why you only have factors on one side.
Yeah.
Okay.
Okay, so you can extract it this way. Now I combine two of my stories, right? So the first part of my story was that I can compute the monodromy of K-difference equation as ratio of elliptic stable envelopes, right? So from geometry. The other part of my story is that I can extract the wall crossing operators from the limits of the monodromy. So the natural question arises is to study this limit when Q goes to 0 for a single factor here, right? So the monodromy is a ratio of two stable envelopes. How would you let's study this limit for a single stable envelope. All right, and the new part of that is that we need to study this limit for non-generic slopes. So we need to study these limits when S is non-generic, when S is exactly sitting on the wall. The generic limit was already known, so it already appears in the paper of Aganadzik and Akunkov. And the claim is that if you consider this limit for generic choice of slope, so when slope is not hitting the wall, what you get as an answer is the K-theoretic stable envelope of your variety. So again, stable envelopes come in many different flavors: cosmological, K-theoretic, elliptic. And in this limit, you just get the K-theoretic one. important thing again, so in this limit I shift scalar parameter by power of q, and then I send q to 0. But I'm not doing anything with scalar parameters. So scalar parameter, I'm not sending them anywhere. And the interesting fact about this theorem of Achenkov and Aganagic is that, again, the right side depends on scalar parameters, the elliptic thing. But once you get a generic limit, no dependence on scalar parameters. Why? Because K-theoretic stable envelope has nothing, it knows nothing about the scalar parameters. Right? And yeah, so this is a K-theoretic stable envelope with a slope S. So if you choose shift by S, you get a K-theoretic stable envelope with a slope S. And K-theory stable envelope depends on some extra choices, which is a choice of a slope. But nothing, so like explicitly, this thing is a matrix, some n by n matrix, whose matrix elements are rational, polynomial, actually, Laurent polynomials in Kähler parameters. No dependence on equivalent parameters, Z, so on. But we've seen that story at the beginning of my talk, right? So if you go, if you're not hitting the wall, you get only something which depends on equivalent parameters. If you hit the wall, you can get something depending on Z. And so we studied this limit, this more general situation with Yakov Kononov. So and again, we wrote a couple of papers about that, but all this story in one slide is the following. So let's say you take a non-generic slope. So you want to take slope on a wall, and more precisely, let's consider the following picture. So let's say I have a wall. Let's S be some point on that wall. Let's consider generic slopes. So by this I mean that I can shift this non-generic slope by some parameter, by some small deformation, so plus minus epsilon, in the direction of stability condition theta. So I can always do that. So I have two non-generic points. Then the result is that something interesting, and I guess it was missed by experts in the theory of stable envelopes, is that if you consider that limit to the wall, then the result, so this is a matrix whose matrix elements now depend on all parameters, on parameter Z, on Kähler parameters, on parameter A, equivalent parameters, and the matrix elements are rational functions, complicated rational functions in both sets of variables. But kind of a miracle which happens here is that this matrix with rational functions always factors into two factors. So one of the factor is the K-theoretic stable envelope corresponding to non-generic slope. So say I took this generic slope here. So this matrix only depends on equivalent parameters. As I said, like for generic slopes, it only depends on equivalent parameters. But the other thing depends only on Kähler parameter, and that is a miracle. So you have some matrix, it depends rationally on all parameters, and this matrix factors into product of two. One depends only on Kähler parameters, one depends only on equivalent parameters. That is a bit unusual, and you can do it from both sides. So you can divide this limit by, say, generic K-theoretic stable envelope after the wall or before the wall. You have two types of factorizations, and in both cases, if this thing is sufficiently close to the wall, right? So there is no other wall which separates it. Then you get this. Then you always get this kind of factorizations. All right. So as I said, the second factor, which depends only on the equivalent parameters, we know who it is. It's a K-theoretic stable envelope corresponding to this generic slope. What is this factor which depends only on Kähler parameters? We can also identify it, and it's K-theoretic stable envelope which describes something on the mirror side. So it's not exactly the K-theoretic stable envelope of a mirror variety. It's slightly more complicated thing. Well, the long story short, it turns out that that you can construct a finite group, which is a subgroup of a Kähler torus which acts on a dual side. How this group is constructed? Well, you take this point on a wall, you take the exponent of that point. It lives in the Kähler torus. So the Kähler torus acts on the dual side, right? So it's equivalent parameters for the dual side. And so this finite group also acts on the dual side. And you look at the set of fixed points for that finite group. So you get some variety which I called y theta. It's some subvariety in the mirror. And what we have here is a second factor. Well, it's a K-theoretic stable envelope with infinitely small positive or negative, depending on the factorization slope for this variety y check. So it's not exactly mirror, it's some subvariety here. All right, so that is the result. And so what is the upshot of that theorem? So if you know that you have factorization like this of a stable envelope, right, in the limit, and you know that your monodromy is a product of two stable envelopes, so you combine these two stories. So now you can construct the limit you want, right? So in the limit, each of these factors factor in 2. So what you get is the formula which will approximately look like that. And so those extra factors which were bothering me at the beginning, they will cancel at this point, and so I get the formula just for one. So I get the product of 4 factors, because in the limit each of these stable envelopes factored in 2. So the factor in the middle, well, it's a ratio of 2 K-theoretic stable envelopes with opposite choice of chambers. So this is what we call in geometry a K-theoretic R matrix. Right? So this is a K-theoretic R matrix corresponding to the dual variety, so it only depends on parameter Z, integer parameter. And well, it gets conjugated by some K-theoretic stable envelopes on the original variety X. But you can get rid of this conjugation. You can switch to K-theoretic stable basis. So this formula is written in the basis of fixed points, so to say. And now if you write it in the basis of stable envelopes, so basically you need just to conjugate by these matrices here, you can formulate the following interesting theorem, is that the theorem is the following. So if you act by wall crossing operator by a basis of in the basis of K-theoretic stable envelopes. But you need to do it carefully. So you take a K-theoretic stable envelopes for the slope right before the wall, right? So S minus epsilon. But then you get some plus in K theory, and you expand it in the stable envelope basis corresponding to the slope right after the wall. And then in this case, the matrix elements of that computations are exactly the K-theoretic R matrix of this subvariety on the dual side. It's kind of interesting. So one thing which I never expected about wall crossing operators, which we constructed with Zakhonkov, and again, as I explained, this construction goes through a complicated construction of a quantum group. Then in quantum group you construct dynamical while group and so on. And then this abstractly, this thing somehow act on the K theory. But you never expect that if you act like this on the basis of stable envelopes close to the wall, that the matrix elements do not depend on equivalent parameters. So it's so if you act like this thing only depends on Kähler parameters. This property of wall crossing operators was very far from obvious in our work. So that is something interesting. So finally, I have 5 minutes, so I just finish this story with this example. So how would all this...
Your time is almost finished. I think we are...
What is this?
Your time is, I think, yeah, almost over.
Okay.
It is, yeah, 45. Yeah, you will please continue.
Okay, so if I have like 1 minute, I can finish it. So, yeah, so let's do real quick the run all the story for the case corresponding to the Hilbert scheme of points. So let's say I start with a variety corresponding to that curve. That's so it's a curve with one loop, Jordan curve. The dual, the mirror of that variety is known to be isomorphic to the original variety, right? So the dual of that is also a copy of a Hilbert scheme. So what is this sub-variety in a mirror which I need to construct, right? So as again, I said that we need to construct certain finite group which acts on a mirror variety, and the fixed locus of that finite group is what I need. So in this case, we take a slope parameter, which is a rational number in this case, so say this rational number a divided by b. You construct a finite group, so it's just a root of group generated by the corresponding roots of 1, so e to the power s. And then this group acts on the Hilbert scheme, on the dual side, just by rotating this loop. So if you look at the pure description of that thing, so this corresponds to scaling of that loop by the corresponding roots of E. If you ask what is the set of fixed points with respect to this action, well, this is the union of a cyclic wheel varieties which I sit inside Hilbert scheme. And this is a cyclic wheel variety given by the order of that group, so the number of vertices here is b. It's the denominator of this rational number. So the upshot is that this variety is non-trivial, might be something non-trivial if b is, I guess it's the other way, so it's supposed to be, if b is less than m. So if b is too big, you get very large, very long cyclic wheel variety, and some of the vertices of this wheel, some of the dimensions of this wheel variety will be empty, so it will be just a collection of points. But for that choices, you have some interesting wheel varieties, and so you have a set of walls. Set of walls, it's a set of rational numbers corresponding to these conditions that denominator is less than or equal than m. So in the case n is equal to 3, for instance, you see this picture here. It's all rational numbers with denominator not exceeding 3. And the corresponding quantum difference equation for the Hilbert scheme, it will be a product, so the anti-fundamental alcove is this one, between 0 and minus 3. You shift it to here and you take a product over all walls, over all wall crossing operators between 0 and 1. So the quantum difference equation for the Hilbert scheme looks like this, where this matrix M is given by a product of R matrices for cyclic wheel varieties, but it's interesting that it's R matrices in different varieties, right? So we have two factors here corresponding to walls 1/3 and 2/3, which are cyclic wheel varieties with 2 vertices, and one wall is 2 vertices, and like one wall which is R matrix for the Hilbert scheme. Again, in general, that is a generalization of that story. So for, say, type A, without loops, you just get dynamical difference equations, quantum Nijnichs-Malevich equations, and so on. But in this example, that is already showing that you may get something new. All right, so I'll stop here. Thank you.
Thank you very much for any question or comment.
You mentioned linear R matrices. Do we unitary
Unitary?
R matrices?
You mean that inverse of R matrix is R matrix at inverse of U?
R matrices is transition matrix for decomposition in terms of stable waves.
Yeah.
So do these matrices is unitary with Rij,
I believe they always unitary. So
sorry?
I believe they always unitary, and that is
Always unitary.
Always unitary, yeah.
Other question? So maybe I can ask a question. So in the final practice, you consider finite group action on the finite segment wheel varieties. Is it only for affine type wave or?
Like all examples I did by hand is
Yeah, for example, type G.
Yeah, I do touch type B, so I couldn't figure it.
You mentioned some stable envelopes for Hilbert scheme of points.
Yes.
Is it connected with McDonald's story?
Well, yeah, in some sense. So there is a story which identifies. You can identify K-theory of a Hilbert scheme with space of symmetric functions, and then various K-theoretic classes corresponds to various symmetric polynomials, and that's basis of various symmetric polynomials in that space. So, for instance, classes of fixed points usually correspond to McDonald polynomials. Stable n-mod corresponds to some Playtistic Schur polynomials, and in this way it's a connection.
Any other question? Okay, now let's thank speaker again. So we will resume in 15 minutes.
No, I tried them. Yeah, I found it.
What sort of is like my impression of the property not was that she was constructing these prototypes.
She told me that there is a possibility to do some combinatorics, but combinatorics demands you to do some work. If you want to write down so that is kind of algorithm.
Like I said, like in my story, I construct Hilbert's equation, but in a matrix form. So, in principle, if I know elliptic stable envelope for something, and I know that it's x by minus integrate, I can construct it as a matrix. As Richard, I had a work with Weber, they constructed elliptic stable envelopes for all types. They proved the newer thing as a remote for this type G map. And this for I can reconstruct this matrix form. And then once you try to rewrite it, then I can do it. I'm not sure if it's actually true, but maybe it's something. So if X from says those functions are complicated,
I guess it was the last line. Which one? Yeah, well, that's a question. The last one. So there's no one else. Okay. Yeah, so like
Just use it just as
there's this story that recently developed by So essentially what he says is that he looks like from his the way he sees his work, that he's looking at this universe and his description of that dynamical bell graph fraction So what he essentially does is that he considers some kind of quantum version of sure value. So he considers a quantum group of, let's say, GLM and GLM. Okay, and they essentially are yeah, exactly. So essentially what he says is that he constructs the by means of this duality of quantum groups, he describes one side as some universal element on the other side. So in the other one. So this is like two representation, you have tensor product, you want to consider that side. What he does is that he considers universal elements in the quantum group mirror and which are made with I think so. He doesn't have the whole description. So what he does is he considers universal
I say that
you have like two zero power representations. You don't say CM, no? You can identify CM with the exterior power, like a different number of tensor product of exterior power of CM. So it takes a universal element of it takes universal element on the other side, and it takes it back by a coproduct. So my question is, how much do you see this story problems now?
Like my view is that this is what you described. This,
Yeah, I think that
so you like in principle, like you can understand quantum from one. On elliptic level, you see both. Some elliptic level stable is the same as that. So in principle, you see this are matrix, you also see that are matrix.
Because for instance, when you take the cyclic group, you make it a type N you still get a type N. So that y yes is again type N. Right?
Yeah. You mean how
Like we don't have this. I don't see exactly how these varieties YS appear in this book. That's
I see. So I guess if he only considers like a classical story, then all walls in the story usually are solved. And so for all walls for like line view varieties, crossing walls correspond to the accessory matrix with some. So it's like a simple root of the algebra and crossing. There's something very but this view variety story, it's the first time much more interesting than which are walls of type of reflection with respect to the gradual which is not
I'm trying to see how close these things are related. Yeah, I believe they're the same. I would like some.
And then you have the so the GLM
construction.
Yeah, that's completely, but so far I can, for example, last week, easy, very easy, like that. Just concept, exponentially overactive, parameter.
Yeah.
So this, my diagram is just the same. So the meters need to be just from.
You say this is
Yeah. But I can define the action with the limit only on the move.
なんかね、そうです。
this one component is this way, then action one. It recovers. Fine.
This construction of this quantum function is also a flat start design of what's in the circuits. Quantum loop is generated by its matrix elements.
Yeah, but I think I don't know the I can recommend why group for me, it makes sense only.
Maybe, yeah, and that
The Coulomb branch is not